Let's start with the idea of capacitors and what exactly they do in the circuit. If you just got a capacitor, and let's say we're attaching that capacitor, this is typically how they're drawn in a circuit diagram. This is just representing the two parallel plates. And in reality, actual capacitors look more like this. It's just this cylinder with a couple of wires sticking out. And the cylinder is basically the two metal plates, but all rolled up into sort of a spiral, I guess, so that it all fits in this compact cylinder. And then the two wires sticking out are these two wires. So you got the capacitor attached to some wires. Let's say there's a little bit of resistance in the circuit, and let's say there's a battery with a positive terminal and a negative terminal. The presence of the battery means what's going to start happening. I mean, if there was no battery, presumably nothing would happen, right? But with the battery, what's that going to do to the circuit? What would you expect to happen here? Yeah, we're going to get current flowing because the battery creates a difference between a high voltage zone and a low voltage zone. And we should expect current to flow from high voltage towards low voltage if the capacitor is not doing anything. And the capacitor is not doing anything yet because it's empty. An empty capacitor can be treated like just wire. So current's going to flow. But as current flows, current is just the motion of charge. So as current flows, we get charge building up on these plates because charge cannot actually cross this gap. You get charge flowing in, charge flowing out. So that means one of the plates is going to start accumulating extra positive charge, and the other plate is accumulating extra negative charge. And what's really happening here is electrons are moving this way. So you're getting extra electrons on this plate, and you're getting not enough electrons on the other plate. But motion of electrons in one direction can be thought of as motion of positive charge in the other direction. And current is defined as the flow of positive charge, even though it's actually the electrons that are moving. So we can just imagine this as positive charge flowing clockwise. But as we get more and more charge building up on the capacitor plates, what does that do to the current? What's going to happen to the current as the capacitor charges up more and more? Yeah, the current's going to decrease. Because if the battery is trying to push more and more charge this way, but there's already charge on the capacitor, the charge on the capacitor repels the charge that's trying to come in. So that makes it more and more difficult for current to flow. So the current is going to get slower and slower and slower. In fact, we can think of this as the capacitor, since the capacitor is pushing back against the flow, we can think of that as the capacitor having a voltage of its own. The delta voltage from the capacitor, it has a delta voltage. It has a pushback because it stores charge. And the more charge it stores, the more pushback you get. So the delta voltage for the capacitor is proportional to the charge itself, the amount of charge stored. And do you have an actual formula for delta V for the capacitor yet? Yeah, or with the idea of capacitance. The main idea is we can just say delta V and charge, since they're proportional, the difference between them is just a multiplier. So we can say delta V equals Q times something, or we could say Q equals delta V times something. Because the whole idea of two quantities being proportional is that one of them equals some constant times the other. So the way we set up this constant is you can define this idea called capacitance. Capacitance is this quantity you can multiply by voltage to tell you the voltage difference to tell you how much charge the capacitor stores. And you can think of capacitance as being like the measure of the efficiency of the capacitor, how good the capacitor is at storing charge. Lots of capacitance means it will store lots of charge for only a little bit of voltage difference. Alternatively, you could isolate delta V by dividing both sides by C. So delta V equals Q times 1 over C. In fact, you could use this as a formula for voltage difference of the capacitor. Strictly speaking, there's also going to be a negative here because the capacitor is pushing back against that flow of current. The capacitor is pushing back against the battery. So delta voltage for a capacitor is negative Q times 1 over C, or negative Q over C. And we can use that formula for any capacitor in the same way that, for instance, delta voltage for any resistor is just negative IR from Ohm's law, and delta V for any battery is plus epsilon. So these formulas can be used anytime you're dealing with any capacitor, any resistor, any battery. Those are the delta voltages associated with each one of those elements. But this is how we calculate the voltage of a capacitor. You can also get more information about capacitance by isolating it. If you solve this for capacitance, somebody mentioned earlier, yeah, C equals Q over V, or Q over delta V. And let's assume we put all this in absolute value so we can not have to worry about the positives and negatives. Capacitance of that capacitor just means this ratio of charge over voltage difference. So it's how much charge you store per volt. So for instance, you could think of this as if you plug in the capacitor to a 1 volt battery, that capacitor is going to build up an amount of charge. The total amount of charge it stores per 1 volt is the capacitance. So like, let's say you plug a capacitor into a 1 volt battery and find that it stores 10 coulombs of charge. That's 10 coulombs of charge divided by 1 volt. So the capacitance would be 10 coulombs per volt. Coulombs per volt would be the units. And we abbreviate that as farads, or capital F. So capital F, farads, is the unit of measurement for capacitance. And again, this is a measure of how efficient the capacitor is. A high capacitance, lots of farads, means it stores lots of charge per volt. And then if you plug it into a different battery, let's say you plug that capacitor into a 5 volt battery instead of a 1 volt battery, 5 volts, that's 5 times as much voltage, so it'll store 5 times as much charge. So again, the amount of charge stored is proportional to the voltage. Or to put it another way, the voltage is proportional to the charge stored. But that's really just because the only reason the capacitor has any pushback in the first place is because it's storing charge. And the more charge it stores, the more it pushes back. Any questions on those ideas so far and the whole idea of capacitance? So with the circuit with the battery and the resistor and the capacitor is gradually going to get more and more charged. And let's actually take a look at the loop rule there. I think we now have all the pieces we're going to need to fill in the whole loop rule. So if we write out a loop rule for this circuit, we can just say all the voltages add up to 0. And going around a complete loop, we're going through the battery, the resistor, and the capacitor. So all those voltages since we formed a complete loop, what do all those voltages have to add up to? Yeah, those have to add up to 0 because we've returned to the starting point. So overall, there's no difference in voltage from this point and itself. And then we can fill in these formulas. Delta V for the battery is plus epsilon, this constant voltage boost. Delta V for the resistor is negative IR. delta V for the capacitor is negative Q over C. That's the pushback from the stored charge. And I find it helps here to add those negative terms to both sides. So we can write this as epsilon equals I times R plus Q over C. Just to emphasize the idea that the battery is providing a voltage boost, and the resistor and the capacitor together sort of use up that voltage boost. Like, let's say this is a 10-volt battery. Maybe you've got 6 volts going to the resistor and the other 4 volts going to the capacitor, because the resistor and capacitor are in series, so they have to split up the available voltage. But exactly how they split it up depends on how much current and how much charge. Any questions on that equation so far? And I also find it very useful here to think of this in terms of the battery has a finite amount of push. Not finite in the sense that it's using it up as time passes, because we're looking at too short an amount of time here for the battery to run out. But the battery, like let's say the battery is a 10-volt battery. That means these two terms together have to add up to 10 volts. There's a finite amount of voltage. If one of them's getting more voltage, the other one's getting less voltage. It's a zero-sum game here, which means the battery can basically be doing two different things. The voltage from the battery can be making current flow, and the battery voltage from the battery can be making charge get stored in the capacitor. But it can't do lots of both. It can have lots of current and a little bit of charge stored, or lots of stored charge and a little bit of current, or maybe some of each. But you can't have lots of charge stored and lots of current flowing at the same time, because that's going to add up to more voltage than the battery has. Is Q over C always negative? Generally, yeah, I would typically write this as negative Q over C. The actual sign of that is going to depend on which direction you're calling positive. In the same way that, for instance, if we call this direction positive, then the delta voltage from the battery would be negative epsilon, because we're going through it the wrong way. And likewise, if we call this direction positive, the voltage on the resistor would be positive IR, because we're going through it the wrong way. But as long as you're talking about the direction against the direction it's pushing anyway, you're going to get a negative Q over C. Typically, I think if you're talking about if your path is going from the positive plate to the negative plate as you go through the capacitor, then the voltage on the capacitor is going to be negative Q over C. Any other questions on that so far? So let's take a look at some possibilities there. Let's say we're looking at very early on, like at the very beginning. At the very beginning, let's say we call this time 0. We've assembled the circuit, we've plugged in the last wire, and current starts to flow. We'll call that instant time 0. So at time 0, the capacitor is empty. In other words, charge equals 0. If charge is 0, what's the voltage of the capacitor right now? Yeah, if the charge is 0, then the voltage of the capacitor is 0, which means the capacitor has no pushback at all. Capacitor is not doing anything since Q is 0. So that means all the voltage of the battery goes to what? Yeah, all the voltage goes into making current flow. The resistor is getting the full voltage of the battery. And if a resistor is getting lots of voltage, then it gets lots of current flowing, a very, very fast current. In fact, we could even write out our new loop rule. Since the capacitor has no pushback at all, in fact, you could basically think of the capacitor as acting like just wire here. An empty capacitor acts temporarily like wire. So this acts like just the battery, the resistor, and wire. So you can think of this as acting like that simple circuit of a loop that's just one battery, one resistor, and then wire everywhere else. Because if you write out the loop rule, Q is 0, so this term drops out, so you just get epsilon equals IR. So epsilon equals IR is our new loop rule. If you solve that for current, you get epsilon over R. So that's the current at time 0, which we would probably call I sub 0. At time 0, we've got this very large current, epsilon over R. The current we'd expect if it was just the battery and the resistor and that's it. Any questions on what's going on at that initial time so far? As current flows, though, current is just the flow of charge. So as current flows, charge is going to start to build up. And as charge builds up, that means Q is no longer 0. You have a Q over C term. What does it tell you about the IR term? What's going to happen? It's going to have to decrease, yeah. We've increased the charge. We now have more charge than before. We have more charge than 0 charge. So that means IR is going to have to decrease. And of course, R isn't changing. R is just a constant resistance of the resistor. So that means the current decreases. We get less and less current. Current is still flowing, so the capacitor is going to continue filling up, but it's going to fill up more slowly because current is the flow of charge. That means we get even more charge, but more slowly, which means the current's going to decrease even more gradually. And eventually we get more and more and more charge, very, very slowly building up, and less current, very slowly decreasing. Eventually, what current would you expect it to get closer and closer to? What's the current going to eventually approach? Yeah, it's going to approach 0. As the capacitor gets more and more full, you approach a point where the current gets slower and slower and slower. Strictly speaking, you never truly get there, because if the current is very, very slow, then the charge is building up extremely slowly, and so you never truly get to 0 current. But after a long time, and for a circuit like this, a long time might just mean like a few seconds, depending on the exact values of resistance and capacitance. But after a long time, we can expect that the current will be approximately 0. We can assume we wait until it reaches a steady state or approaches a steady state. Because this, as it is right now, this is not a steady state. The current is changing as time passes. But if you wait long enough, this approaches equilibrium. This approaches a new steady state with lots of charge on the capacitor and no current, and then things just don't change any further. Or at least they approach this steady state. So let's take a look at what happens after a long time. Mathematically, we'd say we're taking the limit as time approaches infinity. After a long time, we assume the capacitor is as full as it's going to get. The current has slowed almost to a stop. Current is approximately 0, and the capacitor is as full as it's going to get. And that ultimately is why we know the current is going to be approximately 0. If the current was not 0 yet, that means the capacitor isn't full yet. It's still in the process of filling up. But let's try plugging in 0 for current. 0 current means IR is 0, so that term's gone. We just have epsilon equals Q over C. So our new loop rule is epsilon equals Q over C. The resistor acts like it's not even there, because a resistor with no current is not really doing anything. So there's no voltage on the resistor. The capacitor is now getting the full voltage of the battery. So the full voltage of the battery is being used on the capacitor. And like I said earlier, you can use the batteries, or the battery's voltage can be used to make current flow or make charge be stored. Or you can mix it up. You can have some current flowing and some charge stored. Or you can have lots of charge stored, but very little current, which is what we're doing now. Or you can have very fast current flowing, but very little charge stored, which is what it looked like at the beginning. But you can't have lots of both. We've now reached a point where there's lots of charge stored and essentially no current at all. So we're now at the stage where what the battery is doing is making lots of charge be stored. And if you solve that for Q, what would you get? Yeah, epsilon times C. The voltage of the battery times the capacitance of the capacitor. And that's what we would call Q max or Q final. It's the maximum amount of charge that's going to be stored after a long time. And epsilon in this case would be the voltage that the capacitor has. The charge on the capacitor would be epsilon times C. The voltage of the capacitor would be epsilon. Strictly speaking, it would be negative epsilon because it's a pushback. But the idea is after a long time, the capacitor's voltage is so strong that it pushes back with the same strength that the battery is pushing forward. So the battery is pushing forward with a constant push of plus epsilon. The capacitor is pushing back with a push of voltage that gets stronger and stronger as it charges up. At some point, you've got a plus epsilon push from the battery and a minus epsilon push from the capacitor. Those cancel each other out, so there's no more flow because the pushes cancel each other out in opposite directions. Any other questions on that so far? So let's see if we can graph these. If we draw out graphs, and let's specifically take a look at graphs of both current and charge. If we draw out a graph of charge versus time, and also a graph of current versus time, then we know that if we take a look at the starting values and ending values, at the very beginning, how much charge did we have? We were starting with how much charge stored on the capacitor. Yeah, we started with 0 charge, but we started with lots of current, very fast current flowing. So let me mark that on the current graph also. So for the current graph, we started with epsilon over R. For the charge graph, we started with no charge stored on the capacitor yet. But those are going to be changing. Going back to the loop rule we had, epsilon equals IR plus Q over C. We started with no charge, which means lots of current. And lots of current means charge is flowing very fast, which means charge is building up on the capacitor very fast. The charge on the capacitor is increasing very steeply. In fact, we could even look at the relationship between these, because how is current defined in the first place? What is current? What does current mean? What's flowing here? Yeah, it's the amount of electrons flowing per unit of time. Although we're not describing it as amount of electrons in terms of a count, and we're not saying like 50 electrons per second. Yeah, we're really talking about the amount of charge that those electrons carry. We don't want to say there's 1,000,000 electrons flowing past this point per second. We want to describe it in terms of how much charge the electrons are carrying past that point per second. So the current is defined as the rate of change, the derivative of charge. Current means how quickly charge is transferring. So that also tells us about these graphs. The value of current tells you the derivative of charge. In other words, it tells you the slope of charge. Large value for current means steep slope for charge. So a large value for current means the charge is increasing steeply. But we also know that these have to be changing in opposite ways. That sudden increase in charge means a sudden decrease in current, because they've got to add up to a constant. And now there's less charge, or sorry, less current. If the current is weaker, the charge is still changing, but it's changing more slowly. So this is going to be a less steep slope, which means the current is still decreasing, but it's decreasing more slowly. Because a slower increase in charge means a slower decrease in current. We now have even less current, so charge is going to be changing even more slowly. A very slow increase in charge means a very slow decrease in current. And so we get this pattern of starting off steeply, but then approaching slower and slower. In fact, eventually, we know current is eventually going to approach 0. After a long time, the current gets closer and closer to 0. And after a long time, the charge levels off towards a final asymptote of epsilon times c. So that would be the asymptote of this graph. So Q max is epsilon times c. So these would be the shape of these graphs: the current versus time, or the charge versus time graph, and the current versus time graph. Any questions on that so far? And then if we wanted to take a look at the idea of half-life, half-life is just the amount of time it takes to decay halfway towards the asymptote. Not necessarily to half of what there was, but halfway towards the asymptote. So for instance, for current, the half-life is the amount of time it takes to decay to halfway from the original towards 0. So half of the original amount, half of I naught, this amount of time would be the half-life, usually written as capital T sub 1/2. So that amount of time is the half-life. It's the amount of time it takes for the original quantity to go to halfway towards the asymptote. And then another half-life would be the amount of time it takes to go to halfway from there towards the asymptote. So this would be 2 times the half-life. In twice that amount of time, it's gone halfway towards the asymptote and then halfway again. And then 3 half-lives is going to be halfway from there towards the asymptote. So as you go one more half-life, one more half-life, one more half-life worth of time, you go halfway towards the asymptote, halfway towards the asymptote from there, halfway from there. So you're getting closer and closer to the asymptote, but of course you never actually get there. Any questions on that so far? And then for charge, even though the charge is increasing, this still technically counts as exponential decay because it's not going away from the asymptote. Everything's approaching towards the asymptote. Even though it's approaching from underneath, what's decaying really is the difference. How is it possible that it never reaches 0? As the current flows, the capacitor is charging up, right? So if the current gets weaker and weaker and weaker, that means the charge is getting closer to maximum slower and slower and slower. So let's say we're like 1/10 of a coulomb away from maximum charge. That means Q over C is almost epsilon, so there's a very little left over for IR. So the current's going to be going very, very slowly. But very slow current means the charge is increasing slower and slower and slower and slower. So we're getting just a little tiny bit more charge trickling into the capacitor, meaning the Q over C increases extremely slowly and IR decreases extremely slowly. So it's getting closer and closer. Mathematically, it never reaches the asymptote. But in terms of the actual physical situation, eventually the charge gets so close to Q max that there's, let's say, only a few electrons left, or only a few electrons away from Q max. And once you get to only a few electrons, the model kind of breaks down. Like you can't, if you've got, let's say, 3 electrons, weight 1 half-life, you can't have half of that. You can't have 1.5 electrons. So this model kind of breaks down at small values of Q, or values of Q very close to Q max. Also, once the amount of charge or the difference in charge gets very, very small, there are other forces involved other than the electrical forces that also become important. Forces that are very small compared to the electrical forces most of the time, so we can ignore them. But when we get very close to the asymptote, the electrical forces get very, very weak, and so the other forces are no longer really ignorable. So this model kind of breaks down when you get really close to the asymptote. But it's a very good model, a very, very, very accurate approximation for almost the whole time. It only breaks down when you get very close to the asymptote. And also, if you look at this in terms of practicality, typically in a circuit, how would you be able to tell that there's current flowing? For instance, let's say your resistor is a light bulb. How would you know from looking at it that current is flowing? Yeah, the brightness. So if the resistor is a light bulb, as soon as you connect everything, or as soon as you flip the switch to the on position, the light bulb is going to be really bright and then rapidly fade to kind of dim, and then stay dim for a long time, very gradually fading out. And eventually, even though the current mathematically would never get to zero, eventually you get to a point where there's so little current that the light bulb isn't lighting up enough to see. So for practical purposes, the current eventually gets close enough to zero that it may as well be zero, even though mathematically it's approaching it asymptotically. Any other questions on that so far? How would delta V change during these points? Let's try drawing out a graph for voltage as well. Because the thing is, these are two separate graphs. You can't graph charge and current on the same graph because they're measured in different units. We've got coulombs versus amps. But if we convert these to voltages, voltages are the same thing. You can have the voltage of the capacitor and the voltage of the resistor on the same graph. So let's try doing that as well. Let's draw out voltage, or really delta voltage, because that's what we care about. And on this, we can draw out all three of them, the voltage of the battery and the voltage of the capacitor and the voltage of the resistor. And what do those voltages have to add up to? Yeah, those voltages have to add up to zero. And let's actually look at this as an absolute value. Because formally, we've got current is, the resistor has a negative value for delta V, the capacitor has a negative value for delta V, and the battery has a positive value. The battery, though, is always at just plus epsilon. So let me mark epsilon here. The battery is just going to be this constant value of epsilon. The capacitor, though, how much voltage does the capacitor start with at the very beginning? Right, that's going to start at zero because the capacitor's voltage is negative Q over C. If we start with an empty capacitor, that means Q starts off at zero. So delta V for the capacitor is zero. Whereas the resistor, how much voltage does the resistor start with? If the capacitor is not getting any voltage, how much voltage? Yeah, the resistor is getting the maximum voltage, specifically the full epsilon, the full voltage of the battery. Because going back to the loop rule again, we had epsilon equals IR plus Q over C. If the capacitor is empty, this term's gone. So the voltage that the resistor gets is the full voltage of the battery. So that means the resistor is getting the full epsilon to start with. Use a different color for that. So the resistor is getting the full voltage of the battery, the full epsilon. But as time passes, since current's flowing, the charge is increasing, so the capacitor gets more voltage. So the capacitor's voltage is increasing. And notice that these still have to add up to the constant epsilon. So if the capacitor is getting more voltage, the resistor is getting less voltage. And these are going to be changing at the same rate. Over some period of time, you've got an increase in voltage on the capacitor, you've got a matching decrease in voltage on the resistor. And then the capacitor's voltage increases, but more slowly because it's charging up more gradually as time passes. And likewise, the resistor is getting less and less voltage, but that's also changing more and more slowly. And eventually, since the current is dying off towards zero, that means the resistor is getting less and less voltage, approaching 0 volts. Whereas the capacitor, eventually the capacitor is going to have how much voltage? Or what's it going to approach? The charge approaches Q max, but what does the voltage approach? Yeah, it should approach epsilon, right? That the capacitor is getting more and more voltage. Eventually, when the resistor is getting no voltage at all, because no more current is flowing, the capacitor's voltage approaches the value of epsilon. So at the beginning, the resistor is getting lots of voltage and the capacitor is getting no voltage because it's empty. As time passes, though, we eventually get to a point where the resistor is getting almost no voltage because current has almost stopped, and the capacitor is getting almost all the voltage because lots of charge is being stored. Like I mentioned earlier, these are the two things that the battery can do in this circuit. The push from the battery, the voltage of the battery, can make current flow, and it can make charge get stored. Never runs out of voltage. Yeah, we're not. Voltage isn't really a thing that gets used up. Voltage is the push. Like if you imagine a pump in a fluid flow system, the pump is pushing, the pump is creating a pressure difference. The pump doesn't run out of pressure because pressure is just the push from the pump. Likewise, the battery is providing a push that we call voltage. Voltage isn't something that gets used up. Voltage is just the push. When I talk about voltage getting used up in this context, I mean that the current gets some of that, or the resistor gets some of that voltage, and the capacitor gets some of that voltage. Because they're in series, those voltages have to add up to epsilon. The battery's voltage does dwindle over time because the voltage is caused by a chemical reaction going on inside the battery, a chemical reaction that causes A plus epsilon. But we're assuming here that the time periods we're talking about are very short. Like this time period is probably just a few seconds, or at most maybe a few minutes. Whereas the chemical reaction inside the battery is going to gradually die down over the course of hours or maybe even days. So we're assuming that, yes, the battery is eventually going to dwindle in effectiveness, but that takes place over a much longer period of time than we're talking about here. So we're assuming the battery provides a constant epsilon all the time. Can capacitors break? Yes. The way a capacitor could break down, if we go back to the idea that the capacitor is these two parallel plates with a layer of insulator sandwiched in between. In between the plates, there's some material, usually plastic or glass or air, some sort of material that the charge cannot cross. The problem is if you get so much charge on these plates, if you get a huge amount of charge on these plates, there's so much voltage that the charge does jump across because there's just so much extra push on it. So if you have way more voltage on, way more charge stored on the capacitor than it was designed for, then it melts and ionizes the glass or plastic or whatever sandwiched in between, and the charge jumps across anyway. That's usually the breakdown of capacitors, if you charge it way too much. And what happens there is that sudden jump of current flowing through material that was not designed to have current flowing through it is going to cause a huge output of heat, and the resistor, or the insulator in between is going to melt and usually expand. And so that creates this huge pressure and the capacitor just sort of bursts. But if you take a look at typical capacitor design, I don't know if you can see this in the video, but there's this sort of hatching on here, these grooves. Those grooves are a deliberately built-in weak spot, so that if the capacitor breaks, if there's this explosion inside the capacitor, it hits the weak spot first and just goes. And so it's a sort of a self-contained explosion. All it does is pop open rather than exploding and shooting shrapnel everywhere. And of course, the way to prevent this is just don't plug in the capacitor to more voltage than it's designed for. Typically, a capacitor will have a maximum safe voltage written on the side. So you just don't plug it into anything that's going to have more than that voltage. What equations to use? We know that this is going to be exponential. This is definitely exponential decay towards 0, exponential decay towards c times epsilon. So we can write this as exponential decay. And let's try that out. The current, I think, is going to be the easier one because it's approaching 0. So all we really need for that is current at any time equals initial current times e to the something. Since it's decay, that's going to be e to the negative something t. And have you seen what that something is, that multiplier? What that multiplier is going to be? Rho g over AR is what it would be if this were fluid flow, if you had like fluid draining out of a tank. But in the case of the RC circuit, anytime you've got a circuit with a resistor and a capacitor, and optionally a battery, it turns out that the value of this constant doesn't really matter whether there's a battery or not. All that matters is the resistance and the capacitance. If you actually set up the differential equations for that, you end up with 1 over RC here. So the resistance and the capacitance. So that's the constant we're talking about. What this means is if you have a very large resistance and a very large capacitance, that's going to mean it takes a lot of time to get any meaningful sort of decay. Large R and large C is going to mean a much more gradual decay. Because a large resistance means current is going to flow very slowly, so it's going to take more time for the capacitor to drain or fill up. Large capacitance means the capacitor is capable of storing lots of charge per volt. So again, it's going to take more time for the capacitor to empty or fill up. So R and C together, R times C, determines how much time it takes for this change to happen. In fact, RC is the time constant, tau. So if you wait for an amount of time equal to R times C, because resistance times capacitance actually gives you an amount of time, if you wait for that amount of time, this becomes e to the negative 1, because RC over RC is just 1. So e to the negative 1 becomes 1 over e times the original current. That's the idea of time constant. Time constant is the amount of time it takes for there to be 1 over e of the original amount left. Yeah, the whole point of an equation like this is that once you have the equation, you can predict the current at any instant in time. However, you don't necessarily need this equation for everything you want to do. Usually what we just care about is things like after a long time, what's going to happen. So we can see after a long time, there's going to be effectively 0 current. Or if you want to know the half-life. Half-life is just the amount of time it takes to decay to half the original amount. So if you want to know the half-life, you can just say the final amount is original amount over 2. If we say the final amount is the original amount over 2, you can then solve for t, and that tells you how much time it takes to get to half the original amount. You can cancel out the I naught, so you just get 1/2. And then we could even make things a little easier by just raising both sides to the negative 1. Yeah, you could do the same idea if you wanted to find how much time it takes for there to be 1/3 of the original amount or any fraction of the original amount you want. It's just that 1/2 is often a useful reference point because that's what we call the half-life. Also, in this case, I think it would be a good idea to invert both sides, raise both sides to the negative 1 power. That way you get 2. And on this side, you can just multiply these exponents to get positive t over RC. And then how do you get rid of this exponential function? How do you get rid of e to the whatever? Yeah, take the natural logarithm of both sides, so you get T over RC equals natural logarithm of 2. And then multiply both sides by 2, or sorry, multiply both sides by RC. So you end up with the half-life, the amount of time it takes to decay halfway, is logarithm of 2 times RC. And note that RC itself is the time constant. So you can also write this as time constant tau times logarithm of 2. So in any RC circuit, any circuit where you've got a resistor and a capacitor and optionally a battery, you can always find the half-life by multiplying resistance times capacitance times logarithm of 2. That tells you how much time in seconds it takes to decay halfway towards the asymptote. In fact, that's even true if the asymptote is not 0. It's just that the decay we're talking about is decaying towards the asymptote. So you start off this far from the asymptote. One time constant later, or sorry, one half-life later, you'll decay to half that far from the asymptote. And then half of that. And then half of that. So this still counts as decay, even though it's an increasing function. What's decaying is how far it is from the asymptote. Like, let's say we start, let's say 10 coulombs from the asymptote. One half-life later will be 5 coulombs below the asymptote. Another half-life later will be 2.5 coulombs below the asymptote, then 1.25 coulombs below, and so on. So the distance from the asymptote is what's decaying. In fact, I often find it useful to just ignore the usual axis and just treat the asymptote as the new 0. Measure everything from the asymptote. And look at half that distance, and so on. Any other questions on that? All right, then that's about all the time we have for today, but feel free to email me if you have any other questions about exponents or logarithms or exponential functions or capacitors in general. And I will see you next time. You're welcome.